Welcome back to chapter 11. We're continuing on looking at the things that intermolecular forces affect. We're looking at the physical properties of things in the solid, liquid, and the gas phase. And today we're going to start by talking about evaporation, which we could also call vaporization, which is the transition from the liquid phase to the gas phase. The reverse of that, of course, is condensation. How easy it is to make the transition from the liquid to the gas phase depends on the strength of the intermolecular forces between the particles. The stronger the intermolecular forces, the harder it is to make the transition, which means the higher the temperature we're going to see boiling occur. Okay? Now, some terms that we use that you might have heard but not really thought about a whole lot are terms like volatile and non-volatile. Okay? Volatile here doesn't mean they're going to get mad really quick. Volatile means that it can jump into the gas phase fairly easily. Okay, non-volatile means that this substance doesn't want to jump into the gas phase. So, to jump into the gas phase takes an input of energy. And each particle, as it leaves the liquid, takes that energy with it because it's increased its kinetic energy, and that energy leaves and the total energy of the liquid goes down. That's why we talk about evaporative cooling. Okay? So you sweat so that when the water evaporates off your skin, it carries away energy, heat. Okay? Heat of vaporization. Heat of vaporization, delta H VAP, is the energy needed to convert 1 mole of a substance from a liquid to a gas phase at the boiling point. Now, heat of vaporization is going to be a positive value because evaporation requires an input of energy. So, evaporation is endothermic, condensation is exothermic. Exact same amount of energy is going to be released when 1 mole of substance moves from the gas phase to the liquid phase at the boiling point as you see having to be absorbed to go from the liquid phase to the gas phase at boiling point. So let's look at practice problem 11.3 on page 480. All right. So page 480, come on. I should have pulled this out earlier. Hang with me, guys. All right. Let's look at problem on page 480. Okay. If we look at the problem, it says calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. So we've got 2.58 kilograms of water. That means I have 2.58 times 10 to the 3 grams of water. Now I'm going to go ahead and do that because I'm not quite, because I know that I'm going to have to work on things. Okay? Now, if I think about problem solving here, okay, let's scoot over with me. Okay, what I'm going to do is I'm going to go grams of water to moles of water, and then I'm going to use heat of vaporization to go to kilojoules. Okay, so 2.58 times 10 to the 3 grams of water. There's 1 mole of water for every 18 grams of water. So grams and grams of water go out. To go between moles of water and kilojoules, I'm going to need heat of vaporization. Okay, now that's something we look up. So if I look up heat of vaporization, okay, the heat of vaporization of water is 40.7 kilojoules per mole. So the heat of vaporization here is 40.7 kilojoules per mole. So that's what I'm going to use here. 40.7 kilojoules for every 1 mole of water. It's a lookup value. And of course I walk down here without my calculator, so let me punch things through here on my phone, which I don't like using. So, come on. Let's see. 2.58 times 10 to the 3 divided by 18, and then times 40.7 gives me an answer of 5.83 times 10 to the 3 kilojoules. Okay? It's a type of stoichiometry problem. The only difference is this time we're going to use heat of vaporization. Okay? Now, let's talk vapor pressure. Vapor pressure is the pressure exerted by a gas in dynamic equilibrium with its liquid phase. Okay? This is a partial pressure for a specific gas. Now, what do I mean by dynamic equilibrium? A dynamic equilibrium is when two opposing processes are going on at the same rate. So, evaporation and condensation, as we're talking about vapor pressure, because we're looking at the phase change between the liquid and the gas phase. So, in this situation, for every particle that leaves the liquid phase to join the gas phase, a particle leaves the gas phase to join the liquid phase. Now, when we're looking at vapor pressure in this dynamic equilibrium, we are looking at what's referred to as a closed system. It's not an open beaker, it's a closed container. Okay? So let me draw you a picture here to start getting an idea. Okay, I have a box here, and I have a pressure gauge on it. Whee! Okay, so here's our liquid, all down in here. Particles are very close to, close together, but they're in a disorganized kind of process. And a particle jumps to the gas phase here. A particle joins the liquid phase. So I've got some particles up here in the gas phase, and they're moving in random motion. Okay, and some of them are hitting the surface of the liquid, and some of them, when they hit the surface of the liquid, ricochet off. Some of them get stuck. But for every particle that leaves, a particle joins and gets stuck. Okay? So that's a dynamic equilibrium. Now, as we increase the temperature of the system, okay, the forces of collision in the liquid phase go up. And as they go up, it becomes easier to evaporate, harder to condense. So we get a larger number of particles in the gas phase, so the vapor pressure increases. So as temperature increases for a substance, its vapor pressure increases. Now, in picture A here, then I have all liquid, nothing's in the gas phase, and we see wholesale evaporation. In picture B, I have 3 particles leaving into the gas phase and 2 particles joining the gas phase. I've got some in the gas phase now, but I'm still not at that dynamic equilibrium. In C, we've got a dynamic equilibrium. 3 particles evaporate out of the liquid, 3 particles condense out of the gas. Now, if we look at the rate of evaporation, okay, the rate of evaporation is constant, but notice as the concentration of gas particles goes up, over time the rate of condensation increases, and dynamic equilibrium, just to reinforce, is when those 2 processes are going on at the same rate. So, for a given liquid in a container, the pressure increases until equilibrium is reached, and at this point we have vapor pressure. The larger a substance vapor pressure at a given temperature, the weaker its intermolecular forces. Okay guys, here's a graph that shows diethyl ether, ethyl alcohol, water, and ethylene glycol vapor pressure as a function of temperature. Now, if we look at a single temperature here, 20 degrees C, okay, you can see water has the lowest vapor pressure, then ethyl alcohol, and then diethyl ether. Since water has the lowest vapor pressure at a given temperature, it has the strongest intermolecular forces of those 3. Diethyl ether has the weakest. And if we were to bring ethylene glycol in, notice it has 0 vapor pressure at 20 degrees C. So of these 4 substances, ethylene glycol has to have the strongest intermolecular forces. Diethyl ether has to have the weakest. So let me scroll on down here. Also notice that as temperature increases, the vapor pressure of the substances increase. So let's talk about boiling. Now, how would you describe boiling? Think about it for a second. If we were in the classroom, I'd make everybody describe it for me. Okay? If we think about boiling, boiling is when a bubble forms in the body of the liquid and then rises to the top. And then releases. So inside the liquid I got a bubble. Guess what? Inside that bubble we have vapor of the liquid phase. So here we got water, these are water molecules, and that's water vapor inside the bubble. The pressure exerted by the gas molecules on the surface of the liquid, on the outer edge of the bubble, has to be great enough to hold the bubble open. If it doesn't, if it's not enough pressure, this bubble collapses essentially even as it's trying to form. Okay? So the pressure in here is vapor pressure. Now, this has to do with our approach to boiling point. Okay? If the vapor pressure inside the bubble is less than the external pressure above the surface of the liquid, the bubble collapses and no bubble rises to the surface, no boiling. The boiling point is the temperature at which the vapor pressure, the pressure inside the bubble, equals the external pressure. Normal boiling point, is the temperature a substance will boil if the external pressure is equal to 1 atmosphere. The stronger the intermolecular forces, the higher the boiling point of a given substance. Okay? And I want you to remember that boiling point is not an equilibrium situation. As soon as that bubble reaches the surface and breaks free, all of those particles that jumped into the gas phase escape and leave. Okay? Now, here's a pretty little graph, chart. It tells you the elevation of certain locations, the approximate atmospheric pressure, and the boiling point of water. Okay? So Boston, Massachusetts, sea level, okay, has an atmospheric pressure of approximately 1 atmosphere. Boiling point of water is 100 degrees C. But if you are on Mount Everest, the atmospheric pressure is 0.32 atmospheres, and the boiling point of water is 78 degrees C. Okay? So, your tea is not going to be very warm if you're trying to make hot tea on Mount Everest. But you can see elevation makes a difference. External pressure changes the boiling point. So at a specific external pressure, the substance with the lowest boiling point has the weaker intermolecular forces. You can see how external pressure affects things. Now, let's look at that graph one more time that I had in here earlier. Okay? The line drawn here, this horizontal line, 760 millimeters of mercury, or 760 torrs, the same as 1 atmosphere. So what we see is the normal boiling point line. So you see diethyl ether has the lowest normal boiling point, and then ethyl alcohol, and then water, and then ethylene glycol is off our chart. So looking at these three substances, we can say that water has the strongest intermolecular force, diethyl ether has the weakest because it has the lowest normal boiling point. So once boiling point has been reached, all the energy added in goes to the phase transition, increasing the potential energy of the system by moving particles further apart. And the temperature will remain constant until all the liquid has been converted over into the gas phase. Okay, let's look at a pretty little graph here. So if I have a substance, let's say in this case water, and I'm at 20 degrees and I started adding in energy, what we see is the temperature of the liquid increases until we hit 100 degrees C. And at 100 degrees C, the line flattens out. And the reason the line flattens out is because all the energy that we're putting in at this point is not changing the kinetic energy of the system, it's changing the potential energy of the system. Once everybody's been converted into the gas phase, then the gas's temperature increases. Okay, let's talk melting. Melting is also called fusion. It's a conversion of a solid to a liquid. Like evaporation, it's an endothermic process. The heat of fusion, delta H, FUS, is a positive value. The stronger the intermolecular forces, the larger the value of the heat of fusion is for a substance. Pressure plays a minor role in melting and freezing because there is such a small difference in the density of the solid and the liquid phases of matter. Okay? So, I'll talk about water and some special things to do with water, but we'll keep in the back of your head that there's not much volume difference between a solid sample and a liquid sample of most substances. So that means pressure plays a very small role in fusion or freezing. Now, here's another graph for water. in general, let's take a water sample at minus 10 degrees C, as we add energy in, okay, we increase the temperature till we hit 0 degrees C. At 0 degrees C, we see melting. All of the energy that's being put into the system at that point is going to the phase transition, and that's why the temperature holds constant. This is why we put ice cubes in a drink. As long as you have ice cubes in there, the energy that's being absorbed from the outside the glass goes into melting the ice, okay, and not warming up your drink. Once all the ice is melted, you have, diluted drink and a drink that's warming up. Once it's all melted, the energy goes back into changing the temperature of the system. Okay. Scrolling on down. Melting point is the temperature at which you have an equilibrium between the liquid and the solid phases for a substance. Or you could say it's the temperature at which we see a conversion from solid to liquid if energy is added, or the temperature at which we see a conversion between liquid to solid if energy is removed. If you had a 10-gram ice cube put in 10 grams of water at 0 degrees C, and you don't put any energy in, you don't take energy out, you're going to maintain 10 grams of water liquid, 10 grams of water solid. Okay? So if I want it to freeze and get more solid, I would have to start pulling energy out. The stronger the intermolecular forces, the higher the melting point. The weaker the intermolecular forces, the lower the melting point. Now, in general, heat of vaporization is always larger than heat of fusion because there's a much larger conformational change as we move from liquid to gas than from solid to liquid. Think about it. Going from solid to liquid, the particles move a little bit apart. Going from liquid to gas, the particles move way far apart. Okay? So as you can see here, heat of vaporization, heat of fusion. Heat of fusion is much smaller than heat of vaporization for a given substance. Okay? Now, kind of putting things together, we're going to look at what's called a heating curve. Okay? So if we started out with a solid sample of water at 25 degrees C, as I start to add energy in, okay, the water, solid water, get this down, I kind of like to get the whole image in. Okay. So as we start to add energy into this sample at minus 25 degrees C, what we see is that the ice is warming up. There starts to be more vibration, okay, in the ice cube. I think it's kind of interesting the way that they drew it. But we've got a solid. At 0 degrees C, okay, melting occurs. So what we see is in part 1 here, we have a change in kinetic energy of the system. All the energy we're adding in is going to kinetic energy. In part 2, where we have melting going on, the energy we're going in is going to potential energy. The potential energy of the system increases while the kinetic energy stays the same. Okay? In part 3, okay, notice that the temperature rises again. That's because everything's now in the liquid phase and the energy I'm going in is going to make the particles move faster. So we have an increase in kinetic energy. In part 4, where we're at the boiling point, okay, we have a phase transition from the liquid to the gas phase. The energy that we're putting in goes into changing the potential energy, moving the particles further apart. On average, the particles in the liquid here and the particles in the gas phase have the same kinetic energy. And lastly, when we've got it all into the gas phase, the energy I'm adding in just goes to increase the kinetic energy of the water vapor, steam. Okay? Now, I'm not real fond of this image because your true water vapor is just there where it's coming out. That's condensing water. Okay? So it's kind of a sticking point. All right. Now, I often do this math problem, but I'm not going to this time, so we're going to skip over that math problem. So we're going to move on. We're going to talk about a phase diagram. Okay? A phase diagram is a map of the state phase of matter as a function of both pressure and temperature. Within a given region, a specific phase of matter is stable. Okay, so under those conditions, that's the phase that we would see. So let's look at a phase diagram. Okay, here's the phase diagram for water. Notice that the vertical axis is pressure, the horizontal axis is temperature, and notice both of them say not to scale. Okay? So, if I'm at a location right here, temperature and pressure, I'm going to find the solid state of water, and only the solid state of water. If I'm under the conditions right in here, okay, anywhere in here, I have only the liquid phase for water. And if I'm in here, I have the gas phase. Okay? Now, this line right here, called the sublimation curve, and along that line, I would find both the solid and the gas phase. If I cross over this line from solid to gas, we have sublimation. If I go from gas to solid, from a location here to a location here, I have deposition. Okay? The fusion curve, that's the line that separates solids and liquids. If you're along that line, you have the solid phase and the liquid phase in equilibrium with each other. If I went from a point here to a point here, I would be doing evaporation. If I went here to here, I would see freezing. Okay? Along this line right here, okay, it's the evaporation curve. Along that line, we're going to have the liquid and the gas phase in equilibrium with each other. So if I went from here to here, that would be evaporation. And if I went from there to there, that would be condensation. Okay? Now, all three of those curves meet at a single point called the triple point. At the triple point, all three phases of matter are in equilibrium. You find solid, liquid, and gas all sitting there in steady amounts. Okay? And you just see things moving back and forth between the three phases, but the amount in each phase stays the same. So if I put 20 grams of liquid water in there with 10 grams of solid water and 10 grams of gaseous water, then the proportions would stay the same. Okay? Now, out here at the end of the line, so to speak, we hit what's called a critical point. Now, liquids and gases are both fluids. They flow. The particles move past each other. When we get up here to the critical point, something very interesting happens. We can no longer tell the difference between a liquid and a gas. The density of the gas has increased, the density of the liquid has decreased until they kind of merge into what's called the supercritical fluid. Okay? At the critical temperature, no matter what pressure you apply, you cannot get it to condense into a recognizable liquid. Okay? So at this critical point, above the critical temperature, no matter what temperature I apply, I cannot get it to condense into a liquid. Now we're going to talk a little bit more about this in a second, but one of the things I want to point out here is that the fusion curve. Notice that the fusion curve here tilts a little bit back to the left. So notice at 0 degrees C, as I come up here, okay, 760 torr, okay, we hit right there. If I increase the pressure, notice I've gone from a gas to a solid, and if I increase the pressure, I go to liquid. Water is very unique. It's the only substance where the liquid phase is more dense than the solid phase at the fusion point. Okay, this tilts back this way. So I can apply pressure to a solid chunk of water and I can get it to melt into the liquid. This is actually what happens below an ice skate. They put so much pressure on the blade that it actually melts the liquid and it lubricates their travel across the ice. Once their skate moves past that point, it automatically freezes again because there's no pressure anymore. Water is the only substance where you're going to see that line. This is why ice cubes float. Okay? Water liquid is most dense at 4 degrees C. At 0 degrees C, it's less dense than solid ice cubes. So ice cubes float. It's the only solid that floats in its liquid. So I've already told you what the triple point is. Now, talk you through the critical point and supercritical fluids, okay? As temperature increases, the vapor pressure increases inside the sealed chamber, the density of the gas increases, the density of the liquid decreases, and at the critical point, they equal each other, okay? Supercritical fluid. Now here's some pretty pictures. You can see that the temperature is below the critical temperature in the first one. So we have a distinctive gas phase and liquid phase, and you can kind of see evaporation going on there. Okay? As we increase the temperature and we approach the critical point, it starts to do really weird things. I can kind of still see, but you can see that it's getting very muddy. And once we are above the critical temperature, I only see one phase. Okay, it's a supercritical fluid. So the temperature, the critical temperature is the temperature at which you see the transition to a supercritical fluid. Above this temperature, we see no liquid, no matter what the pressure. So I can apply incredible pressures and I can't get it to condense into a recognizable liquid. The pressure at which this transition occurs is called the critical pressure. The term critical is sometimes used to specifically denote the vapor liquid critical point of a material above which the distinct liquid and gas phases do not exist. Okay? At this point, the phase boundary between liquid and gases terminates. In water, the critical point occurs at 647 K and 218 atmospheres. That's way up there. Now, supercritical fluids are really neat. Okay? Now, here's phase diagram for iodine and carbon dioxide. I want you to notice in both of these, the fusion curve tilts to the right, not to the left. And notice that the critical point for carbon dioxide is at 31 degrees C and 72.9 atmospheres. They've been playing with carbon dioxide supercritical fluid as a cleaning fluid. It does a better job sterilizing surgical instruments than does an autoclave. And if we used it to dry clean clothes, okay, there wouldn't be that funky after smell if you got something back from the dry cleaners. Right? Now, I also want you to notice about carbon dioxide that at 1 atmosphere pressure, okay, it phase changes from solid to the gas phase at minus 78.5 degrees C. To go through from solid to liquid, okay, on its way to gas, we'd have to be over 5 atmospheres in pressure. So that's why dry ice is dry ice. So within a region, you have conditions of temperature and pressure that make one specific state of matter the stable state for that substance. Okay? I've already walked you through changing pressure and changing temperature. So let's talk about water one more time. Water is called the universal solvent because it dissolves up so many different substances with a variety of intermolecular forces that it can engage in. It can interact through intermolecular forces with molecules using dipole-dipole bonding, hydrogen bonding, and London forces. Through ion dipole, it can interact with ionic compounds. An ion-induced dipole, it can interact with nonpolar covalent molecules, dissolve up an oxygen molecule or a carbon dioxide molecule. On top of that, for such a small water molecule, it has a very high freezing point and a very high boiling point. And that's again due to its strong dipole-dipole interactions between water molecules and the strong hydrogen bonding. Okay, London force is also important, but all three of those combined really make water unique. Okay? Water is the only common main group hydride that is a liquid at room temperature. Okay, a hydride is a compound that is a nonmetal combined with hydrogen. So notice that water has a boiling point of 100 degrees C, but everything else is much less than room temperature. So all of those substances that you see have boiling points below normal room temperature, which is usually around 25 degrees C. Now, the boiling point of water is way out of line based on the size of the particle. Again, that's because of the really strong intermolecular forces. So water in the solid phase is less dense than liquid phase, and solid water floats in liquid water. This is because of the alignments of the water molecules to get maximum hydrogen bonding in the solid phase. In the liquid phase, they don't line up to give the maximum 4 hydrogen bonds for every water molecule. Okay? For a substance, for most substances, the solid phase is the densest, followed by the liquid phase, followed by the gas phase. Water is at its densest at 4 degrees C and at normal atmospheric pressures. And that means the density of solid water is less than that of liquid water. So ice cubes float. And guys, this is the end of chapter 11 and the end of the material for the first semester. See you second semester and get ready for your last test.